All right, so with that said, that I think is important context for the diaphragm, which will hopefully let you follow along a little bit closer when I take you through the story of the design. So for us, we can do the different checks. We can design with Eurotech. We've got the Simpson guys. I think I saw them on the call as well. So Maddie, so we might give the Simpsons a run. And for the lamellar width, that's going to be important for the in-plane strength. And that isn't always, well, we don't hard code always the lamellar widths, and you might need to speak to suppliers from some of the data like that. So that'll be an input that we get from the Next Timber technical design guide that can be found in any supplier's design guides. So with that said, let's fire up the app. For those new to it, it's a web-based app. A lot of you might be familiar with it by now if you're on this second webinar. But what we're focusing on here is the diaphragm design. So when you click a diaphragm, again, you've got the scope of a personal project or your enterprise. So we've got a lot of enterprise customers now, and you can do it as a shared project. So in this case, I'm going to go CLT Toolbox Design Team. We're going to choose the previous webinar. We're going to go webinar 2, lateral stability and connections, and diaphragm design. So if we look back at this image, what we're designing here is remember there was 4 portions of 4 rectangles essentially that made up the diaphragm, and we're going to design this part of the building here. And you can see here, you've got 12-meter grids, so the panels spanning from left to right, and you can get 3 panels in at 2.67 meters at each grid line as well. So this is the section where we're going to look to design. So when you fire up the diaphragm calculator, you can see the dynamic image populated here on the right, and it is zoomable because the aspect ratios of diaphragms do change from time to time. For us, we're going to start with our Timberlink panel. So let's say we had a 220 panel working based on the preliminary member design you could follow the previous webinar. So you can going through the different inputs, you've got the orientation, so the direction of the lamellas as well. So right now it is in the right direction along the actual length of the joints. So other inputs, so you got the length of the diaphragm. So we're 12 meters left to right, and we're 24 meters top to bottom. And with that, we can actually input our panel widths as well. So again, looks a bit hairy, but when you zoom in, you can start getting an understanding of how it's working. So we've got a half lap connection, and it does update based on the initial connection assumptions. So moving through, you got the panel orientation. I mentioned that, so you can change it in the other direction. And then here is the part where it's going to be iterative design without joint connections. So here we've got a spacing of 150 on our half lap joints. So next, as I mentioned, the connection data, the slip modulus does impact the overall stiffness of the diaphragm and individual panels. And you can either choose a user-defined slip modulus, you can choose the version based on Eurocode, as I mentioned, or you can choose the supplier version as well, and this is based on ETAs. So if we did go, say, for example, partially threaded screw and a 180 panel, but again, you can go back and forth to get that, and that'll get the overall stiffness, as I mentioned. So moving through, you got your design codes. So these are all default inputs because that's specific based on the method. An obvious question is, because we're designing from Australia, New Zealand, it is a performance-based design as well. So you are borrowing from Europe a lot in this case, hence we're explicitly just only having that as the option. So input forces, you can change the lateral force. So for us, we're going to go in the X direction. If I bring back this image, you can see here we're checking for this direction the force with 11.39 kilonewtons per meter ULS and a 7.59 SLS. So let's input our forces. Now this is going to test my memory of a goldfish, but for the sake of not jumping back and forth, let's just input them as our loading. And again, that can be taken from a different workflow outside of CLT Toolbox that most engineers are comfortable with. So strength parameters, we've got user defined right now, but we are working at hard coding it by suppliers, but some suppliers have gaps in this data. Hence, we'll just leave that as a user input here. So some of these can be found explicitly mentioned in the ProHoltz design guide, but I'd recommend speaking to your member supplier to work out what are the in-plane shear values and these 3 failure modes, which I'll also talk you through in a second. So the widths of the lamella data is also important. So again, taking that from the supplier design guide in this case, because again, it's not always explicitly consistent with every supplier, the widths, because they do vary at sometimes more than others. All right, so that's the lamellar width, also impacts the in-plane shear strength. And finally, you got your design data to Eurocode in this instance, and you can follow the more information to understand specifically what there is and get it more to the local context as best you can. So if I go through the calculations, you can see the scope of the check. So right now, as you'd expect, it's a big diaphragm working as one. So you wouldn't expect the utilization to be so high, but I'll follow through the calculations now. So firstly, the in-plane stiffness properties of the CLT, I mentioned before where that's relevant. Looking at the in-plane deflection, so again, the substitute deep beam girder analogy here from Proholtz volume 2, got the relevant section there. You can again see how the forces distribute and the overall assumption. So you've got the lateral load of the SLS, the effective stiffness. Next is the shear stiffness per fastener. So again, moving through here to calculate the case serviceability, also relevant on the densities of the timber. So both of these being the same in this instance, the same panel, but in other instances, they might be two different. Yeah, moving through, you can see the equations. Again, not a black box, we follow it in full, but the equation that's familiar to you, what I showed before, is the panel stiffness, bending stiffness, shear deformation. And because it's a really deep beam, the shear deformation might actually be a bit more than, well, I probably originally expected when QAing this stuff. And then you've also got the connection contribution as well. So bring that all together, you've got your calculations, movement, your panel stiffness as well. So the individual panel by panel, but also the overall diaphragm stiffness. And again, this can potentially be taken into separate software if you wanted to, but at the very least, not a black box. You can actually do a rectangular design in here and maybe work hand in hand with FEM software, because yeah, it's important to understand how the diaphragm's working from first principles, which this can help, I guess, engineers understand. Moving through, you got your actions, your bending moment, the shear force. So a big bending moment's developed, but it's also a big capacity of a diaphragm. And then finally, the strength. So you can see here the different checks, in-plane bending design. So you can work out the stress here. So again, really big moment, but a big diaphragm. You can see the analogy of how the forces interact. You've got tension at the joints as long as, in addition to sliding, so moments creating that force and the shear force in plane as well. So following this, you can see the forces developed along each axis, the axis being the bottom left-hand side of the diaphragm. That's the starting axis. Again, you sort of have to zoom in a bit to understand that. And then you got the forces per fastener. So the joint shear forces, kilonewtons per meter, which can then be taken into the floor-to-floor connections, which I'm about to show you and do a design for. And you can see the joint forces per fastener. So again, the loads developed for the fasteners, so easy transmission to the other calculators. And then following that, you got tension and compression strength within the diaphragm. So that's another check, which I opened with. And then, of course, the in-plane shear verification with 3 failure modes. So one, you're shearing off of the boards as per the Proholtz Volume 1 design guide. So I recommend, reading this side by side again, so you've got a dynamic calculation to the actual manuals that we're working with. Second, in the shearing off failure of glued surface of the joint. So you can see here the glued surface is working in torsion, hence the actual aspect ratio of the width I mentioned before being 115 mil, and taking that from the supplier design guide, impacting the torsional rigidity here, but also the number of glued joints, because each glued joint represents a torsional resistance to help with that check. And finally, the shearing off of the whole entire plate working together as one, and that's again following the Proholtz design guide. So it's a pretty comprehensive design. It's not a silver bullet where you might have penetrations, you have irregular diaphragms, but at least now at the start of projects where I think fasteners are assumed at really, generic, X screws per meter or a volume, and that's lacks the efficiency. But as we actually go to understand deeper and deeper into the actual design, you can start finding that next levels of efficiency. So let's wait for it to print, because at the end of the day, it's the printing of the design report that comes together, and it takes a bit longer in our calculators based on the amount of data that's being saved. As you can imagine here, there's a fair bit going on in these calculations. So you'll also notice our print reports, they're always going to be the right same data as the calculation, so that won't change. But what will change is we are focusing on making them better, more aesthetic, and less space and stuff like that, and more organized. So you can expect that over time.